So for years now, the whole story around AI has really just been about conversation.
A simple back and forth.
Exactly. You ask a chatbot a question and it answers. But what we're watching right now is a fundamental, I think, a decisive shift in the field. AI is moving from being this passive partner to an active, autonomous agent.
We're talking about systems that you give a high-level goal to. So I'm like, audit this 500-page contract and rewrite all the IP clauses.
Wow.
And it just goes off and executes that whole multi-step workflow on its own. It's not just talking to you anymore. It's doing things.
And that transition, that single change, is what introduces this massive computational crisis.
It's a huge crisis.
Yeah.
Exactly. When these agentic systems start working, planning, retrieving data, verifying their own results, they need the model to manage just an immense amount of context for a very long time.
And our current models just can't handle that.
The traditional AI models we've relied on, the dense transformers, they become economically unviable almost immediately. They hit a severe bottleneck.
Which brings us to our mission for this deep dive. We are going to be dissecting NVIDIA's strategic answer to this whole computational crunch.
The new Nemotron-3 family of models.
Scheduled for launch in late 2025. And this isn't just a minor update, right? This is an architectural revolution, and it's designed specifically for this new age of agents.
It really is. We're going to unpack the core technical breakthrough, this hybrid Mamba-Transformer mixture of experts architecture. And just as importantly, we need to understand how this all fits into NVIDIA's sovereign AI strategy.
The idea that they commoditize the software to sell the hardware.
It's a pure infrastructure play. That's the whole game.
Okay, so let's unpack that context crisis first.
Yeah.
Why are these new agentic systems so demanding on the old models?
Well, it really boils down to the workflow itself. An agentic system isn't one single model. It's more like a cluster of specialized cooperating agents.
So you might have a planner, a retriever.
Right, a planner agent, a retrieval agent, a verifier agent, all working together. And they're constantly passing messages and intermediate results back and forth.
So it's not just one question and one answer anymore. We're talking thousands of internal messages that all have to be remembered in sequence.
Precisely. And this constant cascade of communication, it creates an enormous demand for token throughput. It also causes something the sources are calling context drift.
The model loses the plot.
It loses the plot, the context window. Its short-term memory just fills up so rapidly over thousands of turns. If the agent forgets what it was doing, the task fails.
That makes perfect sense. I mean, if you're trying to automate something complex, you can't have the AI forgetting steps 1 through 3 by the time it gets to step 4.
And the primary culprit, the main bottleneck here, is the underlying transformer architecture. It's brilliant, don't get me wrong.
Sure, the attention mechanism, the thing that gives it that perfect recall.
Yes, the ability to look back at any point in history. But that power, it comes at a cost.
A huge cost. And it scales terribly.
It's the Achilles heel.
Yeah.
The compute required scales quadratically. We write that as ON2, where N is the sequence length.
So to make that real for everyone listening, if you double the length of the document you're feeding the AI, you don't just double the compute.
You quadruple it.
And we are now talking about asking these agents to process documents that are 1 million tokens long.
Exactly. And when N gets that large, the compute, and especially the memory for the key value cache, the part that stores every token's representation, it just becomes prohibitively large. It's too slow.
So the whole point of Nemotron-3 was to break that quadratic cost barrier.
Yes, to make long context inference for agents economically viable again.
Okay, so if the transformer is just fundamentally bottlenecked, you can't keep throwing more hardware at it. What's the architectural escape route they found?
They took a hybrid approach.
Yeah.
And the core insight, the real aha moment, is realizing that not every single layer needs that perfect quadratic recall.
You need the power of the transformer for the hard stuff, but you need something way faster for just getting through the bulk of the text.
That's it. And that is where Mamba comes in.
Mamba. Okay, so what is that?
Mamba is based on a concept called state space models, or SSMs. Unlike the transformer, which looks back at everything, Mamba uses a recurrent mechanism. It compresses the history into a fixed state vector.
Like a running summary.
It's a continuous running summary of what it's read so far. And the massive benefit of that design is speed.
It's linear.
It's linear, or ON. So if you double the document length, you just double the compute, not quadruple it. And Mamba is amazing for processing massive data streams really quickly. It's the model's running memory.
But I'm guessing it has a downside.
It can sometimes struggle with pinpoint retrieval. Finding that one obscure detail buried deep in the history, that's where transformer attention is still king.
So Nemotron-3 interleaves them. It finds a synergy.
It's a genius compromise, really. You use Mamba layers for the efficient bulk sequence processing, that's most of the work, and then you intersperse those with transformer layers for when you need that precise quadratic recall for core reasoning.
And what does that actually give us in terms of, performance?
The specs are genuinely groundbreaking for an open model. This design lets Nemotron-3 natively support a massive 1 million token context window.
And the speed.
Critically, the inference throughput is 3.3x higher than a comparable dense transformer model. Even something powerful like Qwen 330B, you get all that knowledge without the crippling cost.
And then on top of that, they double down on efficiency with the mixture of experts or MOE architecture. Let's look at the Nemotron-3 Nano specs. It's got a huge knowledge base, 31.6 billion total parameters.
Right, and that 31.6 billion, that's the storage capacity. That's how much knowledge it's absorbed. But here's the financial game changer. It only activates around 3.6 billion of those parameters per token when it's running.
So it runs with the speed of a tiny model, which is perfect for these rapid, high-frequency agent loops, but it's drawing on the knowledge of a model almost 10 times its active size.
That cost decoupling is everything. It's exactly why an enterprise would consider running AI on their own infrastructure now.
And that ties right back to the strategy. If NVIDIA provides an open model that is engineered to be this financially viable, low-latency, high-throughput, then you have a huge incentive to deploy it on your own NVIDIA hardware instead of paying per-token API fees to a cloud provider.
That's the strategic wedge. It's brilliant.
And for the even bigger versions coming next year, the Super and Ultra, they're introducing another efficiency layer called latent MOE. What is that?
It's all about minimizing memory overhead at massive scale. So think of a giant team of chefs, the experts, working on a meal. In a traditional MOE, every chef has to have the entire recipe book.
Which is a huge waste of memory and slows things down.
A huge waste. Latent MOE splits the model into a common knowledge core and private expert parameters.
Ah, so it's the chefs sharing one big kitchen idea. The common core is the kitchen, and the latent parameters are like each chef using their own private spice rack.
That's the perfect analogy. It ensures memory efficiency when you're routing tokens across hundreds of experts on dozens of GPUs, which is what you need to do to scale up to the 500 billion parameter level.
Okay, before we get into the performance numbers, we have to pause. NVIDIA has used this Nemotron name for 3 distinct generations. And I know that's caused some confusion. Can we just quickly map out the family tree?
Absolutely. It's a necessary clarification.
So first generation was 2023, the Nemotron-3 8B family. These were just standard, dense transformers. Their main claim to fame was introducing SteerLM, which we'll get to.
Right. Then, in 2024, came the giant, the Nemotron-4 340B. And this model wasn't really meant for deployment as a chatbot. It was specifically designed to be a teacher model for synthetic data generation.
And finally, our focus today, the late 2025 Nemotron-3 Family Nano, Super, and Ultra. These are the ones defined by this new hybrid Mamba-MOE architecture.
And the crucial point here is that Nemotron-3's quality is almost entirely reliant on the data generated by that Nemotron-4 teacher model.
The scale of that data is just staggering. We're talking about a training foundation of 25 trillion tokens.
Which, for context, is significantly larger than Llama 3's 15 trillion tokens.
It's immense. And a huge chunk of that, the sources say around 3.5 trillion tokens, was synthetic.
And this synthetic data flywheel is the secret sauce. It's the key to Nemotron-3's efficiency. The Nemotron-4 teacher generated high-quality reasoning chains, data points, which were then rigorously verified by reward models, what they call GenRM.
So you're basically distilling the intelligence of that massive 340 billion parameter model into the much smaller, more efficient Nemotron-3 Nano.
That's the distillation effect. So the Nano, even though it's only activating 3.6 billion parameters, it acquires reasoning capabilities far beyond what its size would normally suggest.
Because it was trained on the concentrated intelligence of a much bigger teacher.
Exactly. And this whole open, transparent approach, releasing massive data sets like Nemotron CC Code V1, that's the foundation of their sovereign AI strategy. They're challenging the closed API economy.
You're saying, run this powerful open Linux of AI on your own sovereign cloud? Shifting gears a bit, let's talk about the enterprise user. For them, control and safety are everything when you're deploying agents into a business workflow. You can't have an HR agent suddenly getting sarcastic. This is where SteerLM comes in.
Yeah, traditional fine-tuning, like RLHF, often leads to these very bland, safe, but useless responses. SteerLM, which they've refined since the 2023 version, treats alignment differently. It's not a binary good or bad problem, it's a multidimensional control surface.
So instead of just aligning the model in a general way, you can specify dimensions like helpfulness, verbosity, even humor. Give us an example of how that would work.
Okay, imagine you need a customer service agent, but also an internal coding assistant. You don't need two different models.
Right.
With SteerLM, you use the same base Nemotron-3 model, and at inference time, when it's actually running, you just dial in its personality. For the customer service bot, you set verbosity to low, maybe a 2, and helpfulness to a 4. For the coding assistant, you crank verbosity and helpfulness both up to 5.
One model serving multiple functions, that's huge for flexibility and cost.
It's incredibly cost-effective. And that flexibility makes the Nano model so essential for scale. The Nemotron-3 Nano, that 31.6B total, 3.6B active hybrid, is positioned as the edge orchestrator.
It has to be fast.
And it is. It uses FP8 optimization, which is a specialized format that basically halves the memory footprint and computation required. It lets it deliver 4x higher throughput than its dense predecessor.
And that's what you need for high-frequency tasks, like summarizing a constant stream of emails or routing thousands of support tickets.
Exactly.
And for safety, they have NeMo Guardrails. How does that system work in an agentic environment?
The guardrails are essential because they're programmable. They provide this external layer of control over the model's output. Developers can write rules in a language called Golang.
So you can enforce strict governance, like if the user asks about competitor products, politely decline.
Precisely. And they also use it to mitigate hallucinations, especially in the reg workflows. The guardrails actively check to make sure the model's answer is grounded only in the documents you provided, which stops it from making things up.
Okay, let's talk performance, because benchmarks are really the currency of these agentic systems. What numbers really matter for an enterprise listener who's looking to automate complex processes?
The number one thing is the ability to execute specific tasks without error. So the instruction following score for Nemotron-3 Nano is an exceptional 99.2%.
And that's critical because if an agent fails to follow a specific format like outputting only in strict JSON, the whole downstream workflow just breaks.
It breaks the chain completely. So that nearly perfect score ensures workflow integrity.
And its ability to use external tools is strong too. I see a 71.5% score on Toolbench.
Right, but the reasoning power is probably the most surprising part, especially considering the model's active size. It scored a standout 92.34% on the math benchmark.
That's a result you'd usually see in models that are hundreds of billions of parameters larger. How does this smaller, more efficient model pull that off?
The team attributes it to an optional feature they call thinking mode. When it's tackling a hard problem, the model could first generate a reasoning block where it details its steps before giving the final answer.
Ah, so it shows its work.
It shows its work. And this is a crucial feature because it gives developers a real dial to control that accuracy versus cost trade-off. Simple task. Use the fast, direct mode. Complex financial audit. You flip on thinking mode for verified accuracy.
That ability to right-size the intelligence needed leads perfectly into the system of models architecture that NVIDIA is pushing. It's not about one giant model doing everything.
Absolutely not. The Nemotron family is tiered to optimize what they call tokenomics, finding that perfect balance between costs and the intelligence you actually need.
So the Nano is the quick, cheap router or edge orchestrator.
The Super, which is 100 billion parameters and expected in the first half of 2026, is the collaborator for high-volume general enterprise work.
And then there's the Frontier model, the Ultra 500B, also H1 2026. This one is positioned as the ultimate reasoning engine, designed to go head-to-head with things like GPT-5 or Claude 4.5.
And this is where you see the final strategic hardware lock-in. The Ultra model is being trained using a proprietary NVFP4 format, specifically to maximize efficiency on Blackwell GPUs. It is built from the ground up for their next-gen hardware.
So if an enterprise wants the absolute cutting edge of Nemotron's intelligence, they are, by definition, committing to the latest NVIDIA infrastructure.
That's the play. And because running a hybrid Mamba-Moe architecture is complex, it needs specialized compute kernels. NVIDIA just abstracts all that away using NVIDIA NIM, their inference microservices.
So a developer gets a pre-built container and can deploy a complex Nemotron-3 API endpoint in minutes.
Without ever needing to understand the underlying SSM kernel requirements, it's about ease of use.
Okay, so wrapping this up, what does this all mean for the future of AI? The strategic implication seems crystal clear. NVIDIA is providing a full, cost-optimized intelligence factory, a system of models where you use the right tool for the job.
They're making the hardware indispensable by perfecting the open-source software layer that runs on it.
And the most profound technical takeaway here is that Nemotron-3 Nano really proves that the impossible triangle of context, speed, and accuracy can actually be solved.
It proves that the quadratic cost of the transformer is no longer an insurmountable hurdle for agents that need huge context windows. The hybrid Mamba-Transformer architecture has resolved the critical bottleneck that paralyzed the old dense models.
So you should really consider this. If NVIDIA, the dominant force in AI hardware, is betting its entire future architecture on moving away from the pure transformer design, will the transformer-only era soon be considered legacy? Will all future frontier models be forced to adopt a hybrid architecture just to compete on speed and efficiency? Something to mull over as you watch the AI agent market heat up.